So I'm going to say a few words about myself to start before I do the conference. So I'm an assistant astronomer at the University of Bordeaux. I did a bachelor in physics and chemistry and then a master's in astrophysics. And then I did my PhD already in Bordeaux on the interstellar medium of local group galaxies, Messier 33 in particular. And after that, I went and did a postdoc at IRAM, Institut de Radioastronomie Millimétrique in Grenoble, where I still observe the interstellar medium, but from our galaxy, much closer, no farther than 200 parsec. And then in 2016, I got a position in Bordeaux as an assistant astronomer. So yesterday, Stéphane talked to you about the CNRS positions in France. We have another kind of position, which are called astronomer and assistant astronomer. And this is intermediate between a professorship and CNRS. So CNRS only do research. Professors do half research, half teaching. And in my case, I do half research, some teaching, not a lot. And also we have things that are called community service. The idea being that if you build an instrument, if you maintain a database, if you contribute to the community as an observer, it's based on observation both of Earth and the universe, then it's counted in your work. So enough about me. Let's talk about a bit about astrochemistry. So today is a two-part lesson. I will be doing the first part. I will go from atoms to simple molecules, and then Vasily Savinogradov will do the second part. So I will stop at protoplanetary disks. So what is astrochemistry? So astrochemistry is the study of the chemical composition of the interstellar medium. It's a very strongly interdisciplinary field. I'll show it to you along the way. And this is the overall outline I'm going to follow. I'm going to need to be able to understand what are the conditions of the interstellar medium before we can do any chemistry in it. So we'll talk about a bit about its composition, what it's made of, what are the physical conditions, the radiative fields and things like that. Then we'll do a bit of observation. How do we observe the interstellar medium? How do you observe the molecules, both in the dust, in the ice mantles, and in the gas phase? And then we'll talk about astrochemical modeling. How do we do astrochemical models to compare with these observations and understand the interstellar medium? And then we'll do a series of focus on astrochemistry in different environments that we can find in the interstellar medium. So first of all, what is the interstellar medium? So the interstellar medium by name is what you find between the stars. So if you take a few hours time of telescopes and you integrate here, you see the stars. You see mostly black between the stars, but sometimes you see light that don't come directly from the stars. You can see different colors. You can see blue light. You can see reddish light here. So the reddish light is going to come from one kind of excited gas, which is the first component that you have in interstellar medium, gas. And the blue light here is going to be diffused light from the stars that diffuse on another component of the interstellar medium, which is interstellar dust. It's very fine dust, more like soot than the dust that you would find or grains that you would find on the beach. And another clue that there is dust in the interstellar medium is when you see dark lanes like that. It's because the dust is a very strong absorber of visible light and especially UV. And so the main composition, if you take the interstellar medium, the gas to dust ratio is about 1%. You get 99% gas and 1% dust. If we look now at the elemental abundances, there's been a few talks about it already. The reference here that is a bit hidden is Asplund et al. 2009. So this is the reference of the sun composition. And you see it's a logarithmic plot of abundances, and there's widely varying abundances for the different elements, with the most abundant being hydrogen and helium, and the rest being orders of magnitude less abundant. So this is why McCall et al. In 2001 made the astronomer's periodic table. If you look at the periodic table for astronomer, it looks like that. There's mostly a huge chunk of hydrogen, a bit of helium, and then the rest is almost only traces. But these traces are very important. You see, if you're a geologist, you see ways of making mantles and rocks. If you're a chemist, you see ways of doing organic chemistry here. And here we saw yesterday the importance of the noble gases to trace the formation of the protoplanetary disks. Now I'm going to talk a little bit about star formation in itself, because it's a complex problem. We could have a whole lesson about star formation, but you have to see it as a cycle of matter through successive stages. It's often showed in this way, where you have a cycle here with arrows of different steps. You go from diffuse gas that is destabilized and starts to gravitationally contract. And in this contraction, you get the phase of the cold dense core, which itself, part of it might become more unstable and condense to a protostar and then a protoplanetary disk at the end. This is a bit misleading image. It's easy to show and to explain, but it's a bit misleading because each step doesn't have a 100% efficiency. At each time, there is energy and matter feedback, and only a small fraction of the matter actually goes into each of the steps. Sometimes the efficiency is higher, sometimes it's a bit lower, but you have to see it as a cycle where all the time you get some feedback and some of the matter go back at the end. You have to remember that at the beginning of the universe, it was the lesson of last year about nucleosynthesis, you only had H and H2, you had nothing else. The first stars formed from H and H2, from H and helium, and nothing else. There were no other elements or really trace elements. And so this cycle of the star formation enriches the ISM in heavier elements. And as you get more and more generations of stars, you get more and more bricks of other elements that we call metals, which are not metals, but astrophysicists call them metals, that you can use to form other molecules. An idea about the physical conditions of the interstellar medium. This is a plot of temperature against volumic density or number density. And you see that you have widely varying densities and widely varying temperatures. But if you look here, 10 to the 19 here would be the room here. Basically, you have 10 to the 19 particles per cubic centimeters in our atmosphere, around 20 degrees. And you see that most of the interstellar medium is very diffuse. The order of magnitude being a few or less than 1 particle per centimeter cubed to a few 100,000 or million for the interstellar medium. After that, this is the star forming phase with densification, and then you reach the stars here. And you see that the main arrows is this densification and cooling of the gas to form stars, but you always have feedback. The dotted lines here can be feedback from the stars themselves, either end of life or during their life, but also during the star formation phase, you get feedback all the time. So this concludes the first introduction about what is the interstellar medium, and now I'm going to talk about how we observe the interstellar medium. First of all, I talked about what kind of matter we have in the interstellar medium. I'm going to talk about what kind of radiative energy we have in the interstellar medium. If you take an average measurement over quite a large band of wavelength, this is a UV and this is a millimeter wavelength, you don't see a flat spectra. This is the energy density, and you see several bumps. And each of these bumps come from a different component of the interstellar medium, or or even the stars. So starting from high UV, you see that you have the first bump here that peaks in the UV. It's the very young stars. There are not a lot young stars, but they're very important for the heating of the interstellar medium and for very strong UV radiation that will kick off the chemistry in some region which are called photodissociation region. I'll talk about it later. Then the second bump is the old stars. Old stars is because less massive stars are going to live for a long time. So this is why we call them old stars. They've been here for a long time and they'll be here again for a long time. And this is a peak that's from the visible, but peaks actually in the infrared. And then you get this blue part, which is comprised of two parts. A very regular part here, which is actually heated dust. So the UV photons here, when they interact with the dust grains, they heat it up, and this dust grain then will re-radiate as a black body, but at much lower temperature. So this is why you have here a black body for the stars, several thousand of degrees, and here a black body for the dust, which is 10 to 100 degrees, depending on the places. The part here is the pHs, polycyclic aromatic hydrocarbon. It's much more jagged because they are macromolecules, but they are small enough that you can see the individual vibration bands of the species themselves. Here is just black body emission. And then the last part is not the interstellar medium. It's the cosmic microwave background that is a remnant from the Big Bang. So long time ago, but it's still everywhere and all around us. Okay, so this is what is in the interstellar medium, but how can we observe it actually? So I aligned it here with a plot from ESO, where they put the different telescopes with here the transmission of the atmosphere. So if you have zero transmission here, the atmosphere is opaque at this wavelength. You cannot see anything, you cannot see through the atmosphere. And you see that it's mostly opaque at high energy, from the X-rays to UV. This is also the ozone layer protects us from this strong UV. There's a clear window here at visible light. Okay, this is why we can see the stars and see the sun. There's another big window here in the radio domain, which is closed again because of the ionosphere later on. But between the visible and the radio domain, it's complicated. There are some narrow windows where you can observe, but most of the atmosphere is opaque, so you cannot see the interstellar medium. So this is why we have to make telescopes so that we can go in space and remove the atmosphere. And so you see here, to observe stars from the ground, it's okay. But if you want to come and start observing the dust, it starts to be complicated because it's going to be opaque. So, what instruments do we use? I'll first talk about observing molecules in ice mantles. So, you know that when you go to the interstellar medium, the dust particles are the model of dust particle is a core, refractory core, and then on top of that you can add molecules, volatiles, and we observe them in infrared vibration transitions in the infrared domain from basically 3 to 25 micrometers. And to give you an idea of the evolution in the last years of this field, until 2020, the largest telescope we had was the Spitzer telescope, which was only 85 centimeters diameter. And since 2021 now, we have the James Webb telescope, and it's been a huge jump because now we have a 6.5 meter telescope observing at these wavelengths in the interstellar medium. So the James Webb telescope looks like that. It's actually too big to fit into a payload fairing of a rocket. So you have to fold it. This part here was a 3-part folded. This part here was folded at the back. And this here, it's a huge, actually for scale, you have a Spitzer for scale. You have a standard here, banana for scale, and we all learned yesterday that the best way of doing scaling is to have a geologist in the field. So here you have a standard geologist for scale. So these telescopes are huge, and they are huge, and just for the collecting area, JWST is 50 times larger than Spitzer. So we're going to be doing completely different science with JWST. So what kind of science do we do for observing molecules in the interstellar medium? We do absorption against continuum infrared background. We cannot do emission, well, at least not in the cold interstellar medium, because these transitions would need to be have energies that would require much higher temperatures. So we could not observe them in a cold interstellar medium, but in absorption we can observe them anyway. And so what we do is that we find a field where we think there is dust. We look at the stars that are in that field, and we look at their spectra. So if there were no dust in front, we would see a continuum that is something like the dotted lines here. So this is data that comes from the Ice Age early release science of McClure et al. Actually, here there are two sources, a gray one and a blue one. So focus on the color part of the graph. So the continuum itself, if there were no dust, would be the dotted line. And you see a lot of features of absorption, some of them very narrow, for example, for CO2 and CO. Some of them much wider. Some of them have different vibrational modes for a given molecule. You see the water stretch mode here, the water bend mode, and the water libration modes that are farther away here. But it's complicated. It's complicated because sometimes, for example, if you want to observe ammonia, it's hidden actually inside of the silicate band, which itself is not has a certain shape, which is not Gaussian shape like you would have, for example, for these ones. You have a lot of effects. The fact here that, for example, you have an asymmetry between this part here and this part here of the edge of the CO2 band is probably an indication of grain growth. Then you need to have some me-scattering. It's very complicated, and it's a new science. So it's the first time we've seen these kinds of spectra from space. We have some samples in the lab, but we need to compare them both. And the difference also with Spitzer is that Spitzer might have one part here with worse signal-to-noise ratio, but now we're getting these kinds of spectra against hundreds of stars in one single field, which means that we're going to be able to probe the chemical composition within a cloud of the dust mantles. So how do we observe molecules in the interstellar medium? For that, we're going to have to do a bit of spectroscopy. The interstellar medium is mostly cold, so it's a spectroscopy that appears in the rotational transitions. First of all, the molecules need to have a dipole moment. If you want to observe them, the homopolar or two symmetrical molecules are going to be invisible. For example, in the millimeter domain, you will not be able to see CO2. There are no transition lines of CO2 because it's too symmetric and there's no net dipole moment for this molecule. Whereas for water, it works very well. You see that there is indeed a net dipole moment because of the different electronegativity of oxygen and hydrogen. The second point is that because of quantum mechanics, the rotational energies of these molecules, these ones, are going to be quantified. You see here the different energy level for simple rotor. This is very simple molecule, just to give you an idea of how it works. And there are also selection rules. I mean, radiative transition can only be, for example, in these kinds of molecules, between adjacent rotational levels. So in the end, if you check what are the possible radiation transitions and the energy levels, then each molecule has a unit set of lines. For example, if it's a simple rotator, it's regularly spaced lines, but it can be a much more complex spectra, rotational spectra. And which means that, in theory, since each molecule has a different set of lines, we should be able, by doing spectroscopy, to identify the different chemical composition of the interstellar medium. The first interdisciplinary point I want to make is that, for example, for this, we cannot do it if we do not have spectroscopists that actually measure in the lab some of the transitions of a given molecule, model the Hamiltonian and fit it to the few lines they observe and extrapolate them to the whole domain where we want to observe it in the millimeter domain. So there are some names of spectroscopy database like the CDMS in Cologne or the GPL in the US. And the Splatalog is a big catalog that centralizes a lot of the other catalogs. But so how do we observe them? What kind of instrument do we use to observe a millimeter rotational transition in the interstellar medium? So I said that it was a very low energy transitions. so a few tens of Kelvin. I think it's a tenth of it's a tenth of a kilojoule per mole, so it's very small. And so we need to observe them in the millimeter range. And in this range, this is a bit of a zoom of the picture I showed with the transmission of the atmosphere. You see that at lower frequency, around 1 millimeter, and 3 millimeter, there are some windows between very strong oxygen lines where we can observe, where the atmosphere is transparent. But as you increase the frequency, it becomes more and more complicated. There are water bands where you cannot observe. And even there, between the bands, it depends a lot on the precipitable water vapor, on the water vapor content of the atmosphere. If you have too much water, you cannot observe. And these are small values. So you need to go to high altitude to have less column of atmosphere. And you need to go to desert, very dry places. And then you can open some of the windows. You see here, if you have less than 1 millimeter of water vapor, you can open the window here that was closed before. And so what kind of instrument we use? We use radio telescopes. We place them on top of mountains. And we have two types of telescope. We have a single dish telescope, where you have a unique antenna. And then, the angular resolution is going to be of the order of the wavelength divided by the diameter of the telescope. And here you have typical angular resolution of 30 arc second. If you use a telescope, optical telescope, without any adaptive optic, you're going to get 1 arc second resolution. And if you get adaptive optics, you're going to get much better than 1 arc second resolution. So actually, we don't see that very well in the interstellar medium. We're a bit myopic. We don't see very well. And to get higher resolution observations, well, one way would be to get a larger dish. But it starts to be complicated because you need to have the precision of the dish here that needs to be paraboloid to a fraction of the wavelength. And basically here, this is a 30-meter antenna here at Sierra Nevada in south of Spain, above Granada. And you have a precision here of a hair width, random RMS precision, over 30 meter. And that's the limit of what we can do. It's difficult to do that at a higher antennas. So we were going to simulate higher antennas by doing interferometer. We're going to combine the lights from different telescopes, that are typically a bit smaller, and we're going to spread them out on larger distances, up to kilometer scales. Which means that we get an equivalent resolution, which is typical of the distance between the telescope instead of the size of a single telescope. And this means that we can reach resolution, even sub-arc second resolution. If you go to higher frequency, also it helps. This also remains as a diffraction law. And it means that, for example, in ALMA, you can get higher resolution at the same resolutions. So what kind of molecules do we observe in the interstellar medium? So this is a bit of a busy plot, and it's becoming busier every year because new molecules are detected all the time. This is from the Cologne spectroscopic database, and they say that we should use sentences like in the order of 330 or 300 molecules are detected, because since they appear all the time, we cannot get a definitive answer about the number of molecules. We detect them all the time. So as of February, a few hours ago, there were 332 molecules detected in the interstellar medium, or circumstellar objects. You see here at the column is the number of atoms in the molecule. So this is the diatomic molecules, and then you increase 3, 2, and then this is above 12 atoms. And the first thing you see that there's some kind of distribution. You have a histogram here, and you see more small molecules and less larger molecules. We can have a look at some of the molecules here, and let's try to zoom in. It works great. You see that you have the usual small molecules. Okay, you have HCl. Okay, it's been detected. CO, which is the most abundant molecule in the interstellar medium. And then as you increase the size, you start to see some a bit strange molecules. You see some strange cyanopolines, for example, where you're going to get long chains of saturated carbon with nitrogen on one side and hydrogen on the other side. You're going to see some very strange radicals. You're going to see some C7H, okay, molecules that you wouldn't even be able to maybe synthesize on Earth, but you see them in interstellar medium. So the conditions are very different. We'll see that when we do some modeling than what we have on Earth. But you also, as if you go to the left here, start to see maybe some of your favorite molecules. There's some methanol somewhere. There's some acetic acid, and then you start to get more and more complex molecules. Okay, we start to call them complex organic molecules. We've set a limit, I think, around 6 atoms. Someone did a review in 2009 or something like that, saying that above 6 is a complex organic molecules. Okay, and biologists laugh at us, but that's okay. We don't mind. And also you see more and more saturated molecules. And sometimes you see molecules that you could start to recognize with names like dimethyl ether and things like that. Are we going to stop detecting molecules? Have we detected them all, or are we still on a slope, positive trend for detection? So this is a plot taken from a talk from Pepe Sernicharo, which is one person who is detecting the most molecules at the moment. And you see, as a function of time, using different telescopes, so you see the peak time of telescopes. For example, Kitt Peak was the best telescope to observe in the 80s, and then in the 80s the telescopes like the IRAM 30 meter arrived online, and then some sub-millimeter telescopes new with new receivers or higher antenna started to arrive, and you had typical slopes here of 1 to 2 molecules per year, and it doesn't seem to be stopping. And the big change in the last years has been the Quixote project, so led by Pepe Sernicharo, that uses, and so why are they getting like 4 new molecules per year? What changed? Well, what changed is that they went to a different frequency domain, a bit lower, the Q band, around between 20 and 50 gigahertz, which had not been really observed before. And also what they did is that they increased a lot their bandwidth. So now in one go they can observe tens of gigahertz, whereas before you had to go 500 megahertz by 500 megahertz very slowly to map and to do a spectral survey. Now they do, and so they in exchange of doing setups one by one, they just integrate on a full setup, and they reach really low sensitivities, and so they can detect molecules that are much less abundant. And so this is why here there's this huge acceleration here by more than a factor 2 of the number of new molecules per year. And they are publishing every month. We get new detections of molecules. But actually, you also need to have a spectroscopic background to be able to do that, and have colleagues in spectroscopy lab where you can send them ideas of, I think I've detected the molecule. Can you check if indeed is this molecule or not? It takes a group effort to be able to do things like that. So what do the data actually look like? This is an example. Okay, it's maybe an extreme example, but it's to show you how difficult it is to get information on new molecules, new complex molecules. Because actually the ones that are detected here are detected in cold dense cores, and they are not that complex. We're not reaching the edge of complexity, but there are new molecules that are just less abundant, but they are not too big. Here it's more in the case of massive star formation, so it's hotter, and there's been more possibility of doing chemistry, and so you have huge amount of lines. And actually, so this is a plot of the full 3 millimeter band. You go from 80 gigahertz to 115 gigahertz. Was one of the windows that we could observe through the atmosphere. And you see here is actually the same data, but we are zooming in on the antenna temperature scale, which is an intensity measure we use. And you see here, if you go from 0 to 100, you see a few bright lines. And then when you start to zoom in from 0 to 5, and especially from 0 to 1, it's a forest of line. And actually, we've reached a level where even if you integrate more, you're not going to get lower baseline, because actually the baseline is not noise. The baseline is smaller lines. They call it pseudo-continuum, because you're reaching a point where even if you integrate more, you're not going to get more information about weaker lines. So this is why they call it confusion-limited surveys. And this is a problem to increase the complexity of the molecules we detect, is because that in the sources where we think we're going to find complexity, it's too complex. We're starting to have lines everywhere. And actually these lines here, some of them can be identified, but some of them are still unidentified. And for unidentified line, it's difficult to know if it's indeed a new molecule that you want to detect. It's complicated to see patterns here. If you had one molecule, we could identify patterns. Spectroscopy could tell you it's this kind of symmetry, but here there are lines everywhere. So we do it step by step. We identify the most abundant one, remove them, and then try to find new ones. But actually, when we talk about the people who work on these kinds of surveys, they think that the lines that they observe, some of them might actually come from vibrationally excited, rotational transition in vibrationally excited modes of very simple molecules. And these have not yet been measured in the lab, so we are a bit stuck here now to get new complexity. So this was the part about observation. We're going to go to the second part about how we model the interstellar medium. How do we try to recover the abundances? So I've skipped all the part where we go from the position of the line to the actual quantity of matter, the abundances that we detect in the interstellar medium. Because I didn't have time to do that. But there are ways. We do forward model, where we do modeling of knowing the spectroscopy and physical parameters and a given abundance. We can simulate a spectrum. And we invert that. It's a bit complicated because there are a lot of parameters, because it depends both on the chemical composition and also the physical composition of the region you're observing. If it's hotter, if it's denser, it's sometimes out of equilibrium radiative transfer. So it's not easy, but I would need another half hour to present it. So I'm just going to assume that now we have a composition for an object and we want to simulate it and see if by chemical principles we can get back to the observed abundance. So I'll start by dust. And so the models of dust, they've been created to fit some of the constraints. We have a lot of constraints on dust, and a lot of different constraints. We have dust constraints about the extinction curves in the far UV, how the dust actually differentially absorbs light in the UV. There's a UV extinction bump that you need to explain. There are some mid-infrared emission. There are even infrared emission bands, the one I've showed you before, that are not compatible with black body, but that you need to explain. And for that, we need some very small, you see this is a fraction of a nanometer scale, carbonaceous grains in the interstellar medium. And here the frontier is not clear about when you start to have an aggregate of PAHs, a cluster of PAHs, or a grain in itself. And so A here is for amorphous. So it's amorphous carbon or amorphous hydrogenated carbon, and you get the whole range between things that are more graphite or diamond-like, which would be pure carbon, and things that would be much more saturated, where you would get other level. And they need a mixture. They cannot explain it with a simple composition. What they also need is to get the infrared absorption bands and the visible mid-infrared extinction and the sub-millimeter emission at larger wavelengths. They need not only grains that are made of carbon, but they also need grains that have silicate cores. So this is also amorphous silicate, different kind of composition, and they have mixtures to, as best as possible, recover the shape of all these constraints here. And this here still is in the most diffuse medium. There are no volatiles that are stuck on the grains, but they still need it to do that. And they also need to have some things where even on a silicate grain, you start to stick an outer edge of some soot and carbonated matter. When they increase the AV and you go to a more extincted region, higher density region, and you go from the more diffuse ISM to the more dense ISM, you get an evolution of the grains. You start from the grains that I've shown before, the amorphous silicate and the amorphous carbon. They are photoprocessed. They are here submitted to a strong UV field. And then as you go to more dense ISM, you have an accretion of an outer edge again of a different type of carbon component. And then what becomes interesting, I think, for me, is that when you get the ice mantles that arrive, you start to get some coagulation. So you get clusters of these very small grains that begin to make larger grains. And you also get mantles of ice that I'm going to focus on just a bit later. And that helps, as Alessandro said in his talk, to glue the small grains together. So how do we model actually gas and the gas phase and the ice mantles of the ISM? We don't model the refractory core. In our case, we take them as a given. Like the Themis model do the refractory core, and we are going to add on them a volatile mantle and its interaction with the gas phase. So we include as many microphysical processes that we can think of. I'll talk to them about them in detail a bit later. And we do that in a framework of rate equation, even though sometimes Monte Carlo simulation would be more appropriate, but the rate equation enables us to have a large number of reaction and do some chemical dynamic kinetics with it. And we make a big chemical network with it, and we try to solve the equation. We couple the gas and ices through processes that go at the interface. And basically, what the code does is that it integrates the kinetic first-order differential equation from a single starting point of given abundances at the beginning. And the typical input parameters that we have of our models can be possibly time varying, the density, the dust and gas temperatures, the cosmic ray ionization rate, and the UV extinction. It's the basic parameters that we use as input in our models. Okay, a bit of detail about how they actually work. There are 3 levels that we need to stack to be able to do these simulations. The kinetic chemical models themselves are actually just solving these equations. So it's big networks of reactions. Basically now we have something like 800 to 1,000 species and 10,000 reactions between them. And so typical names in Bordeaux, we do the Nautilus code. In London, they did UCL Chem. In the US, in the team of Rob Garrett, they do Magical. But basically, we all do the same thing. We solve these kinds of equations. Then there's the reaction network. What actually are the values that we put here for the different reaction rates, and what reaction do we actually take into account or not. Some of them have barriers, some of them are endothermic, so we need to filter all of the possibilities of the combination of all 100 molecules with other 1,000 molecules, 1,000 molecules. And so, again, this is where we need our physical-chemist colleagues to tell us what reactions are possible, what reaction won't happen. Some people do experiments, I'll talk a bit later. Some people do computations. And we get these kinds of networks. This is a very small part of the network. It's an old paper where at the time you could still graph some subparts of the network. Now it's much more complex. But you see that from oxygen here, you can go both ways with starting to ionize or get some radicals. And of course, all of these are linked because CO appears here and CO appears here. So the network itself is completely linked with all the molecules. And for typical names of reaction networks, we have the KIDA reaction networks and the UMIST reaction networks that you can check. They are mostly standard in the ways they present the data. So even with a given model, you can cross-check with different networks to see if they have influence. And then the reaction rates themselves are actually temperature dependent. So we need to store that information. And for that in Bordeaux, we have the KIDA database, which is the kinetic database for astrochemistry, where we store all kinds of reaction rates, both from the lab, from computation, and we do aggregate of all this information. And we do the work of, if we have several rates for a given reaction, doing a consensus with experts to get a single value to put into reaction network. But we still keep all the data. We compile everything so that also if people who want to do new experiments can go check what other people have made. And it's complicated because, for example, you see here, these are some observed values, so measured, for example, by Astrid Berja in Bordeaux, of a reaction. I forgot to write which one it was, but they all look the same, almost all look the same, as a function of temperature. And you see here the possible parametrization of the rate as a function of time. That could be possible. And what we're interested actually is this part here, very cold interstellar medium. And depending on if indeed there are some tunneling effects or quantum mechanical effects, you can either have slightly strongly increasing or strongly decreasing rates at low temperature. So we're always trying to get new data to get more information about these things. We try not to fit the rates from observations of interstellar medium molecules. We try to go to first principle and talk to our chemists colleague to get most data, but it's difficult. I mean, one experiment here could take 1 year for one system. One reaction, it could take almost 1 year, a month, and we need tens of thousands. So we work by analogy and also that, but in evolving field. So actually, how do we get these values? Be it for the measuring points, so it's lab work. People do some experiments where they can have supersonic flows, or they can have crossed beam or almost parallel beams where they actually measure the reaction rates at the condition close to the interstellar medium, sometimes down to a few tens of Kelvin. And we also have people working in computational chemistry that can also measure these kinds of reaction rates. So it's second point where interdisciplinarity is very important for astrochemistry. So for the gas phase chemistry, we can neglect three-body reaction. We are not in the atmosphere. We don't care. It's only by molecular reaction. It's easy. And there are two classes, basically, of things that happen in the gas phase: two-body reactions and photoprocesses. So this is a bit of a table of giving you the typical rates for the kind of reactions. The first one that you could think of maybe would be neutral-neutral reactions. Okay, we get two neutral species, we make them react, and hey, we get a new molecule. Actually, it's not that easy. Because the rates, typical rates of the coefficient can go from negligible, because sometimes there's actually an activation barrier along the reaction path. And for example, if you get H2 plus O, well, it won't react at cold interstellar conditions because there's a 3000 Kelvin barrier. So it's not going to happen. This is not how you get OH in the cold interstellar medium. But for other molecules, like example CH plus N, it's barrierless, and then you get typical 10 to the minus 10 rates. Ion neutral reactions are much more efficient because they are most of the time barrierless. And for example, you get an order of magnitude quicker reactions for this. Okay, so this is a rate here. you have to multiply it by the concentration of both of the reactants to get the actual rate in seconds minus 1. So it can be fast in theory, but if you have no reactants, it's not going to be fast. There's also electronic or electron recombination, where you get a cation here and you make it react with an electron. You could expect that you would just neutralize and get the neutral large molecule, but actually it's very energetic, so you break everything. It's not a way of constructing new complex molecules, it's a way of breaking everything. So for example, here you have ionized formaldehyde, and when it reacts with an electron, actually everything is broken. But they are very efficient. So they happen all the time, and there's always the interstellar medium is always slightly ionized, so these reactions happen a lot of the time. You have some radiative associations which are very difficult, they are very, very slow. You see here several orders of magnitude lower here. You need to emit a photon exactly at the right moment. It's complicated. It doesn't work in the interstellar medium very well. Sometimes when it's the only thing, then it becomes the most important reaction, but it's very rare that it's the most important reaction. And for the photoprocesses, we have two kinds. You have the photoionization. For example, C2 plus a UV, you get C2 plus. So it's a way also of making ions that you need for the ion neutral reactions and to have the fast reactions. And we also have photodissociation. And here the rates are typically 10 to the minus 9 to 10 to the minus 10. But this is for standard ISRF, so for a molecule in a typical interstellar medium that has not been shielded by dust. And actually, most of the time, there's a lot of dust. And so the actual rates are much lower because there's no UV that arrives. This is the rates where you would have a typical UV, which is not what you get in most of the regions. But sometimes, very close to bright stars in PDR regions, there can be very important reactions. So what is actually the importance of grain for chemistry? Why do we do grain and heterogeneous chemistry? Why is it important? Well, if you look at the time scale, for even dense regions, okay, for dense 10 to the 4 and 10K, the mean free time between collision is actually 2 months. Okay, so this is a number. Actually, we have time, okay, for millions of years, but what it's important to compare with is if you look at the typical timescale of diffusion of, for example, hydrogen on a surface of a typical grain of 100 nanometers, it's the orders of hundreds of seconds. It goes very fast. So actually, if you manage to put two molecules on the grain and one of them can move at least, then they're going to react much faster than they would have in the interstellar medium. So actually, the grains are catalysts of the ISM chemistry. In certain conditions, they are catalysts of the interstellar chemistry. And so what are the surface processes? So there are many more actually than the gas phase processes. There are also photoprocesses. You can photodesorb or actually photodissociate. Photodissorption was thought to be very important at the time because in the first experiment, we thought that actually the molecules could come out as pristine. If you irradiated methanol, you could get out methanol. It's more complicated than that. You seem to break a lot of things. It's like a bit of electronic recombination. It's not that easy to get the molecules intact when you leave them out. There's diffusion, there's desorption, and I will go a bit in more details now. So the first step is you have to get your molecules onto the grain. You have to make them stick onto the grains. This is physisorption. We don't have enough energy to actually chemisorb the molecules on the surfaces. So this is just physisorption. So they are trapped into a local minima of the potential field of the surface. The rate will increase with the gas density and the gas temperature because the velocity is a bit higher, and the grain cross-section. Okay. Remember that you have a distribution of grain sizes. So I showed you the very small grains and the very large grains, but you have many more small grains than large grains. So depending exactly on the distribution you want, the surface can actually be dominated by the very, very small grains. Up until now, until recent year, we usually use sticking coefficients. So the probability of a molecule sticking when it comes to a grain of 1. We said that as long as a molecule reaches the surface, it will stick. And actually, there's very recent papers of a team in Marseille, Caroline Stader et al., that show that it's actually not the case. If you look at this is lab work where they put molecules and bombard a little cold, very cold target of gold, of olivine crystals, or even ISM-sized grains. And in that case, actually, on the gold, it sticks all the time. But if you look at the other, it doesn't stick that well. So we might have to refine our models. It's not going to change a lot of things. It's going to change the time scales at which you deplete all your gas. But still, it's interesting that what we thought was the standard that everyone used to be equal to 1, now that we have new measurements, we actually see sticking coefficient that could be an order of magnitude lower on real analogs of interstellar grains. Then once the molecules are on the surface, you need to make them react, but you need to keep them on the surface. So there's a tension here based on the Langmuir-Hinchelwood mechanism in physical chemistry. So you have physisorption of species followed by diffusion and reaction. So it's parameterized by a desorption diffusion energy, which is basically a level of energy at which molecules can start to move. And that diffusion desorption energy actually increases with the species mass. So larger species won't be able to move as easily as light species on the surface. And it also depends on the surface composition. So it means that it's becoming very complicated to model correctly these energy desorption energies, because the composition of the ice changes as you build the ice. So actually the later molecules won't stick the same as the first molecules that arrive on the pristine grains, for example. And basically, if it's too cold, nothing moves. And if it's too hot, nothing sticks. So you need intermediate temperature where the molecules stay on the grains, but they also move. And this is the range of temperature where you're going to have efficient surface chemistry. And you have to remember that it's highly dependent on the mass, and the mass of the species are highly variable also. And so if you combine the fact that H is about 10 to the 4, 10 to the 5 more abundant than any other species on a grain, and the fact that H is very mobile, some molecules, all of the other species are stuck and H is very mobile, it means that most of the surface chemistry is going to be dominated by hydrogenation reactions of species that are already stuck on the grain and cannot move to make themselves larger molecules. So you get hydrogenation chains, for example, where you start from atomic carbon and then you build up these strange radicals to reach a saturated molecule like methane. Same thing for water. This is how we make water in the universe. We make it on the grains, basically. And in the case of CO, that can be created in the gas state before. If it sticks on the grain, you get first partially saturated formaldehyde and then fully saturated methanol at the end. Another processes that we have, I talked about thermal desorption. So you heat the grain and the molecules desorb. There are other ways to desorb molecules, which are called non-thermal desorption. It's all of the ways that you can get a species out of a grain without heating the grains. And so there are many ways. There's photodesorption. I talked a little bit about it. There's a bit of chemical desorption. Actually, if you have an exothermic reaction, you can get some of the energy of the reaction when you build a molecule that a fraction of it is ejected and doesn't stay on the grain. The efficiency is not very high and it's not very well constrained. And you get the interaction with cosmic rays. So cosmic rays are nuclei of molecules. There are some protons, but there are also larger atoms that are accelerated in the interstellar medium and that can interact with a grain. And when they do that, they can do sputtering. They're just so energetic that they pull some of the species out of the molecule, out of the grain, or the grain can explode. They can heat locally the grain, so it's kind of a thermal desorption, but because of localized heating by an interaction with the cosmic ray. And you can also have secondary electrons by the interaction, and you can do some radiolysis of your grain. But this is very new processes. It's processes that we are adding in the models, and they are not very well constrained now, but we used like the Ganil particle accelerator to bombard some ices and to get some yields and have information about that. So this was an overview of what kind of modeling we can do. And now until the end, I'm going to talk about astrochemistry in the different steps of star formation, the one I've showed you at the beginning. So we're going to go from diffuse gas, dense interstellar medium, we're going to go through the PDR phase. It's not a phase, but it's a very important part of the interstellar medium, the photo-dominated regions. And then I'll stop here at the protoplanetary disks for this talk. So the diffuse ISM. It's not easy to observe. Even in optical, it's not easy to observe because the main trace of the diffuse ISM is going to be that the stars are going to be slightly less bright because they are going to be a bit attenuated. But if you have a field of stars, one way of having a less bright star is to have a star that is slightly further away. So it's very difficult to disentangle extinction and distances. So it's not easy. It's easy to measure high extinctions. Okay, you see no stars. It's easy. But low extinctions are very hard to measure. And people who do actually astrophotography, sometimes amateur astrophotography, are starting to get very long poses in certain parts of the sky. And we actually see the dust, not in absorption. Okay, we see that some of the stars here behind might be missing. It's difficult to see that. But actually, we see the dust that is diffusing the light from the whole galaxy. This is places at high galactic latitude. And this is how we know that there's dust here. But to look at the molecules there, it's complicated. The density is very low, less than 1,000 particles per centimeter square. The temperature is a bit higher, and the UV radiation is typical, which means that it's mostly atomic and ionized species. You're not going to get large molecules. They're going to be destroyed by UV radiation. But if you use very sensitive absorption studies against quasars, so you take a quasar like a very bright source in a millimeter, and you try to see if the line are not in emission but in absorption in front of the continuum of the quasar, you actually detect, even in quite diffuse region, CO, HCO+, CF, C3, so there's a review by Harvelis et al. And actually they're already, even in this region where there's supposed to be a lot of UV and it's complicated, you still start to see molecules. So it's not completely atomic. It's simple molecules, a lot of ions, and you're dominated by gas phase chemistry. The grains are too hot. Nothing is going to stick on them. There is evidence of depletion of elements onto the gas grains already in the diffuse phase. So you saw that the Themis model explained that you had grains that are built of carbon and you construct them. But even for the other elements, this is a nice paper from 2009 by Jenkins. He studied gas phase absorptions of a lot of elements, I think he had 20, against a lot of different regions that had different densities. And then he managed to get the differential grain composition as a function of density. So how does the grain differentially, the species differentially incorporate into the grains already in the diffuse interstellar medium? And the depletion varies between elements. You get some of which have very sharp slopes, and some of them which are mostly flat. Okay, nitrogen doesn't seem to be incorporated at the step of the diffuse gas phase, but magnesium and silicium are very depleted right from the start. Now the photodissociation regions. So the photodissociation regions are the interface between hot ionized regions and colder molecular gas. So actually they are everywhere. As long as you have a summer ionizing source, since the dust will try to, will absorb some of the lights, if you go along line of sight, then you get less and less UV, and at one point you're going to reach the cold molecular phase. So PDRs are everywhere. And PDRs are a very wide name because the densities can range from diffuse ISM densities to 10 to the 9, almost protostar-like densities. The UV irradiation can be a few, like standard interstellar medium, to 10 to the 5 or 10 to the 6 if you are ultra compact H2 region. So an O-type star has just been born and is ionizing extremely strongly the gas that is just next to it, even before it's being pushed out. And the temperature is actually determined by the local UV field. So in that case, so this is an example, standard example of the Horsehead Nebula. So farther north here, for a few parsecs away, there's a O-type star that is ionizing. So every time you see reddish colors here, it's because it's H-alpha recombination line of ionized hydrogen. So it means that you at least had UV photons larger than 13.6 eV because you ionized hydrogen and then you see the recombination. And the interface here is, in that case, quite sharp, where you go from a very diffuse, very hot gas to a much colder and completely obscure ISM. And so how do we model that? We do PDR models, which are going to at least be one dimension because you have broken the symmetry of the problem. You now have incoming direction of the UV field. And so in these kinds of models here, the ionizing flux comes from the left. The amount of remaining UV decreases as you go towards the right here because the UV is absorbed by the dust. And so you go through different phases. So on the right side here, you have the temperature, which is shown in dotted lines here. So you start with high temperatures. It's even higher in the ionized phase. The plot here starts in already atomic phase. And it can go down to very cold interstellar medium phases here. And you get different regions. So they're a bit arbitrary, but if you follow, for example, the hydrogen, you go from fully atomic hydrogen to fully molecular hydrogen somewhere around here. In that case, it depends on the density, depends on the temperature, and of course on the UV radiation field. In the case of carbon, if you look just at very simple carbon chemistry, you go from fully ionized carbon to neutral carbon, atomic carbon, to CO, which is going to be the main reservoir of carbon in these objects. And even further again here, the CO is going to go down because it depletes on the grain. And if you look at the electron fraction, the ionization fraction, it's very high here, and it's almost the same as C+, because actually most of the electrons come from the ionization of C+. And when C+ goes down, it reaches very low values of 10 to the 8. So there's a very sharp contrast of ionization state between these two parts. And so there are many, many different kinds of models to try to explain, because there are so many different kinds of PDRs, dense ones, diffuse ones, and so on. Cold dense cores, because these are my favorite objects. The cold dense cores are the first step of star formation. And why do we know there are cold dense cores? Because actually when we look at fields of stars, there are places where we see black holes. Okay, they are not the black holes that massive objects, but there are places where there are no stars. So there could be two hypotheses. There could indeed be no stars in these regions, or it could be just a mask, and it's the correct explanation. It's a region where there's so much dust here that it blocks the light from the stars behind. The extinction, which is the amount of light that is removed from behind, is so high that we actually don't see the stars through the dust. They are very cold because light doesn't reach into them, so the UV cannot heat the grains and cannot heat the gas by photoelectric effect. So it's very cold. They are quite dense. If they were not dense, they wouldn't block all the light. And they have high extinction. Okay, you don't see them. So basically, no UV reach the inner parts. So very particular. They are anti-PDRs. Like they have no UV, almost no UV. And so what kind of chemistry do we have in these sources? We have chemistry that basically everything is going to stick on the grain, and the grains are too cold, and there's no UV to bring them back out, and everything just sticks on the grain, and you build huge mantles on your grain surfaces. So this is simulations done by the Nautilus code by a few years ago, where we see the composition and the amount, so it's measured in a number of layers of ices on the surface. measurement of the amount of ice that we built. And you see that after a few 100,000 years, you start to build these huge 100 monolayer ices on top of the bare grains that you had before. And the composition is depends quite a lot on the temperature, exact temperature of the grains, because what's complicated also is that because of the desorption energies, the chemistry on the grain is very dependent on thresholds. If you're above a certain threshold, things start to move, and you can make, for example, if you manage to be able to move C and O, you can make CO2 ices. If it's too cold and you never go through that phase, then they will never move, and you will get almost no CO2 on the surfaces. And so you get composition, which are water, CO, some CO2, and not a lot of nitrogen. The nitrogen reservoir on the surfaces is not well known. And so an interesting thing about cold dense cores, they seem to be simple like that, but actually it's interesting because they have similar conditions. They are cold, they are dense, but they show varying chemical composition within a cloud and between clouds. And this is because the chemistry in the stellar medium is highly out of equilibrium. So the history of how you reach physical condition is as important as the physical condition themselves. And we showed that by using MHD simulation of a galaxy, where we our colleagues who do magnetohydrodynamic simulation extract a small part and then re-simulate it at higher resolution, and they actually can simulate the formation of these dense cores. And they give us the traces of all the particles that reached this core, and we can simulate here. So this is the trace that they give us. All the particles here reach the dense core phase, so high opacity, high density, low temperature, but not all of them arrive through the same way. Some of them have here, for example, very low density phase before going to high density, and some of them have a slightly higher density phase before reaching the high density. And we do simulation with our models for all of these tracks. And what we find is that indeed, for a given end density, so here within a cloud for one color here, you can have wide orders, like 5 orders of magnitude difference for some molecules. And the only difference for given here density is how you reach that, if you've been through a dense phase before or not. It's the same for a lot of molecules. Of course, the main point here is that there is depletion. Okay, if you increase the density, more quickly you stick everything on the grain. So the main trend is going down here, but the variability here is very high. So now we want to observe many dense cores and many molecules to be able to quantify this variability. In cold dense cores, we also observe actually some complex molecules, okay, so methylformate and dimethyl ether, and for this they've been detected in 2012. Actually, it was quite complicated to, at the same time, understand how they could have formed, because they cannot form in the diffuse phase, that's too much UV. In the cold phase, normally the precursors should not move on the surface, so it's difficult to make them. And even if you make them, when we observe them, you observe them in the gas phase. So it's difficult to understand how you would be able to redesorb such large molecules in region where the density is the temperature is very low. So this is why there's been a development of non-thermal desorption mechanism, because they could be enough to explain how we get some of these so large molecules. And so cosmic rays come mostly from supernova as accelerator. Actually, we have people now working to see if at the edge of supernova remnants, some of them are near molecular clouds, we see a different chemical composition than the ones that are more isolated. Now I'm going to talk about the hot core phase. So I just put this slide again to show you where we are. So the globules are the dense cores that I've just shown you. The PDRs and the diffuse cloud were here. And now we're going to go through that phase. So there's been a gravitational instability, and we're going to form a star at the end here. And so the protostar here, there's a phase where you're going to have heat heating of the star as the density increases. So this is the phase that I'm going to talk about now. In that phase, the people who model them, for example, the team by Garot et al., they do that by a warm-up model. You see here that as a function of time here, the temperature increases from 20K to 400K. And in their models, what they find is that the species, in particular the radicals, they can start diffusing on the surfaces before they desorb. And so they can start to make large molecules. So I'm going to talk about two examples here. If the dotted lines here are what happens on the grains, and the solid line are in the gas phase. So if you look at the example of methanol, I've showed you that it's formed actually in the cold dense core phase. So it's already there at the beginning here. And it just waits here, reacts a bit with the other one. It's one of the reservoir of the ices. It's very abundant. And when it reaches here this temperature, well, it goes out of the grain and it goes into the gas phase. But in the case here, for example, of in yellow here of methyl formate, actually there's no at the beginning. You don't see any. It's not formed. Marginally formed in the dense core phase. And you have to wait until the precursor here, which would probably be something like HCO radical and CH3O radical, start to move on the grain so that it can react. The new molecule is still stuck on the grain, so this is why it's here. And then it desorbs here. Actually, it desorbs here almost with everything, because it desorbs just when the water goes out. So the water is evaporated and everything goes with the water, because the water is mostly the matrix of your ices. So when you desorb water, you desorb everything, almost everything. And these hot cores, hot cores are for high mass star formation, and hot corinos are for the typical small stars like the sun formation. This is where we observe the highest complexity in the ISM. For example, I took the latest, most complex one measured in these kind of sources, and for example, 2-methoxymethanol in NGC 6339. And this is the kind of plots that I talked to you about before. It was a zoom here. And you see that you get a lot of lines. Some of them are other species that are more abundant. But if you do a full model of the thing, then methoxyethanol is the purple line here. You see a line here. This one is actually hidden by here. It's blended. This one also. But you can get a coherent model of all the lines at the same time and convince yourself that you've detected all the lines that are detectable, and you don't have emission at places where you don't expect lines. So you need to be a bit rigorous, but in that case, I think it's a detection of methoxymethanol. And I'm going to finish with protoplanetary disk, going very quickly because it's much more complicated. Cold dense cores are very nice. The temperatures are low. There are not a lot of processes. Here it's very complicated. So I took this picture from a recent review by Karin Oberg in 2023. If you want to check out protoplanetary chemistry, it's the title of the review, I think. And you have many different processes. We've heard about snow lines. There's UV desorption. Then actually there's the protostar itself has some luminosity. There's accretion on the star. The variability of the luminosity of the star actually can vary quite a lot. Can have bursts of luminosity, and then it goes down again. There are turbulent flows. There's infall of cloud material. It's interesting to see that in this community, the infall arrives from the midplane on the outside, whereas Alessandro showed us that in his community, the infall is much closer to the star. So maybe it's a different way of seeing, because in his models, it arrives so close to the star that whatever complexity you had before, I think it's going to be going to vanish. In our case, maybe because it's wishful thinking, we would like to have some of the complexity maybe to be kept and incorporated into the disk. I don't know what is the real answer. Wait a few years for that. And what do we detect in protoplanetary disks? Actually, we detect not that many very complex molecules. Because the protoplanetary disks, well, they are small. They are really small. I mean, like they are 50 AU. And the cold dense cores I've showed you are like orders of hundreds of thousands of AU. So even if you have a nice telescope, it's still going to be very small in your beam. And even if you want a small beam with interferometer, you lose sensitivity. So actually, in the millimeter domain that we detected most of the molecules, but they are actually quite small molecules. Some isotopes and things like that, but maybe the most complex one is probably this one here. Some of the molecules have been detected in infrared and far infrared, but they're also very simple. It doesn't mean they're not there, but it's difficult to observe them. And also the protoplanetary disks tend to be quite cold. So it's not easy also to observe in the gas phase molecules if you have cold dust. And the parts that are warm are even smaller, even more complicated. So this is the end of my presentation. The 3 points I wanted to emphasize is that astrochemistry is an interdisciplinary field. So we need spectroscopists, we need chemists, we need a lot of people actually to be able to build our models. Without them, we couldn't do it. The observation complexity in the ISM is limited both by sensitivity, because we see that when we get more sensitive instruments in certain regions, we can detect new molecules. But it's going to be limited also by the confusion limit. And it's going to be difficult to go beyond this confusion limit, because you reach a point where there's lines everywhere. And so you need better databases to eliminate everything that is not what you're interested in, the actual complexity of the lines molecules you're interested in. And last point on modeling, you have to remember that ISM chemistry is very out of equilibrium chemistry, and the composition is influenced by how matter evolves from the previous steps of star formation. So actually you need to theoretically keep the full history of how you create a core, or even maybe how you create a protoplanetary disk, to understand the actual composition of at a given physical parameter. And since it's an interdisciplinary field, it's sometimes not easy to follow the literature. So 8 years ago, we built this newsletter, which is called the Astrochemical newsletter, that you can subscribe here. And more importantly, you can submit your abstracts. We take abstracts from the physical chemist community, from the observing community, from the modeling community, so that we can exchange and have a better information about all that is done around the astrochemistry. So thank you.